In this lecture, we will learn about Keras. We will learn what Keras is and learn how to install Keras. And we will learn about basic Keras syntax and what binary classification is. Keras is an open source library that provides Python interface for AI frameworks. To put it a little more simply, Keras is a deep learning library based on various deep learning frameworks. It does not support GPU acceleration, and it uses the GPU acceleration features of other deep learning frameworks. Until version 2.3, various deep learning frameworks were supported. But since version 2.4, it has been integrated into TensorFlow 2. Keras provides a modeling library that makes AI modeling easy for AI researchers. Keras allows developers to build AI models without knowing how to use other frameworks. First, let's install Keras. Activate the Conda virtual environment T1 you created while installing TensorFlow 1 last time. Then, type conda install Keras into the console to install Keras in that environment. Keras was initially developed as a machine learning library that works on top of a math library called Theano. However, because of its simple syntax compared to other deep learning frameworks, Keras has become very popular with AI researchers and engineers. Since then, the Keras open source community has grown, and Keras started supporting other frameworks besides Theano. Theano is a Python library that supports mathematical operations of matrices. Researchers at the University of Montreal have developed this open source library, and the usage of Theano is similar to TensorFlow 1. You don't need to know how to use Theano. Just know that Keras works on top of a framework like Theano that supports GPU acceleration. As Keras became popular, Keras also supported the TensorFlow backend. At that time, TensorFlow 2 version did not exist. In TensorFlow 1, when implementing an artificial neural network, developers had to implement all functions themselves. Theano had the same problem, and people who couldn't understand and implement the functions that go into artificial neural networks had hard time using these frameworks. However, Keras became very popular because it provides many functions used to implement artificial neural networks in an easy-to-use, organized way. Because Keras is easy to learn and easy to use, many people outside of AI technology also started using it. Google too recognized that TensorFlow 1 was difficult to learn and use and borrowed Keras to TensorFlow 2. Eventually, Keras is now absorbed into TensorFlow 2, and update of TensorFlow 2 continues. Google has absorbed Keras into TensorFlow 2, but there are some differences from Keras. For example, the structure of the library has changed. As a result, existing Keras code is often difficult to reuse in TensorFlow 2. Today, we'll use Keras to build an AI that classifies real and counterfeit banknotes based on banknote information. Before we start, let me tell you what data we're going to use. In this lecture, we will use a machine learning dataset published by UC Irvine. Among them, we will use the banknote authentication dataset. This data has measurement information extracted from banknote photos and information on whether the banknote is a counterfeit banknote. Today, based on this data, we will build an AI model that uses only measurement information to determine whether a banknote is counterfeit or not. For implementation, we will use Keras, and we will use a small supervised learning-based artificial neural network. Since the data to be used is paired with measurement information and whether or not the banknotes are counterfeit, let's train the model with backpropagation. Binary classification refers to the task of dividing any data into two groups. For example, the task of determining whether something is true or not can be viewed as binary classification. The AI model to be implemented today is also responsible for distinguishing between counterfeit banknotes and real banknotes, so it can be regarded as an AI that performs binary classification. Please download the data from the following link first. The data is a file in TXT format. Each line contains measurement information of one banknote and a number indicating whether the banknote is counterfeit. The meaning of the numbers in one line in order is as follows. The last class is a number indicating whether it is a forgery or not. If you open the data in a text editor or code editor, you will see the following numbers written in the file. In the last lecture, I mentioned that deep learning frameworks utilize data in ND array format. Currently, the given text file also needs to be converted to an ND array. Transforming the data so that it can be utilized in deep learning framework is called data preprocessing. If you look inside the file, the data is separated by commas and line breaks. A text file with data delimited by line breaks and commas is called CSV format file. The CSV format is widely used for storing data, and you will see it a lot as you study deep learning technology in the future. Our goal is to convert data from a CSV format file to ND array data. There are several ways to read a CSV file in Python, but in this lecture, we will read the data from this file using a function provided by NumPy. NumPy provides a function called loadText. This function reads data from a file in a specific type and returns it. Let's take a look at the following code. Write and save the code shown in the slide in the folder where you saved the banknote data. Move to that folder in the terminal and then run code. The loadText function is a function that reads any file and returns the internal data as an ND array. Since the data of the file we want to read is in comma-separated CSV format, set comma as an argument to the delimiter parameter. And if the type of data to read is set to numpy.float32, the data of the file will be stored in ND array as a float32 type. If you run the program, you can see that the file is normally loaded into the data variable. Each line of data becomes one ND array of 5 floating point numbers, and these ND arrays exist in an ND array called data. The neural network we will build today is a model based on supervised learning techniques. In order to train this model, we need to prepare several input and correct answer pairs. If we look at the previous explanation of how the data in one line is structured, we can see that the number at the end of each line is a number indicating whether the banknote is forged or not. Therefore, the last number in each line becomes the correct answer, and the first 4 numbers become the input, which is the measurement information of the banknote. Now, let's separate input and answer to create training data. If you think of the data variable as a 2-dimensional matrix, the last column is the answer. Now, let's create a function called split_last_column that splits only the last column in data. The function shown in the slide is a function that receives a 2-dimensional ND array, stores the last column in a variable called class_col, and stores a 2-dimensional ND array excluding the last column in input data and returns them. If you're curious about how to handle ND arrays in the future, you can get help from a search engine. If you use NumPy a lot, you may remember the functions you use a lot. But you don't have to memorize all the functions provided by NumPy. Now, let's add this function to the code we wrote earlier, and then call the function by passing the data variable as an argument. If we print and check the values returned by the function, we can see that input and answer are well separated as we wanted. Now, let's check the shape of the ND array. ND array has an attribute called shape. This attribute holds the shape information of ND array as a tuple type. If we print the shape of input data variable, we can see that there are 1372 data, and there are 4 measurement information and 1 data. Now, let's create an artificial neural network model using Keras. Write the code shown in the slide first and save it. Keras provides 2 ways to implement a model. One is functional and the other is sequential. You do not need to know the difference between the 2 implementation methods or the functional API in detail. In this course, you only need to understand the sequential implementation method. First, if you want to implement a model in a sequential way, initialize the model instance as a sequential class. When implementing a model using the sequential API, each layer of the neural network is attached to the model. An artificial neural network is made by connecting several layers of neurons, and an artificial neural network with a lot of layers is called deep neural network. Implementing a model in this way is much more understandable and intuitive than in TensorFlow 1. First, we will attach a layer called dense to the neural network. In the last lecture, we learned about fully connected layers, a layer in which one output is connected to all neurons in the next layer is called a fully connected layer. And in Keras, it is called a dense layer. To explain the layer added to the model earlier, we created a layer that fully connects 4 data inputs into 10 neurons in the layer. When creating a model using the sequential API, you must specify input shape when creating the first layer. Even if you do not specify the input shape other than the first layer, Keras determines the input shape of the next layer by checking the output shape of the previous layer. Input shape means the number of ports through which one input data is received. In our data, there are 4 measurement information, so the input shape is 4. Last time, we talked about the sigmoid function while learning what the activation function is. However, there are several other activation functions, one of which is rectifier, which is also called ReLU. The rectifier function is often used as the activation function for hidden layers. Of course, you don't need to understand this function mathematically. In the next layer, a new dense layer is added. There is only 1 neuron in this layer, and the activation function of this layer is a sigmoid function. And if you check the code, there is no layer added to the model behind this layer. In other words, we implemented a 2-layer artificial neural network. Although a 2-layer neural network is not called a deep neural network, we finally implemented an artificial neural network in Python. The last layer in an artificial neural network is called the activation layer. The output of the activation function of this layer becomes the output of the model. In binary classification tasks, the sigmoid function is used as the activation function of the last layer. Also, the sigmoid function is rarely used as an activation function for the hidden layer. If we express the neural network implemented in Keras graphically, it is as follows. The 4 inputs are fed in one-to-many correspondence to the 10 activation functions. The outputs of the 10 activation functions are combined in the next activation function, and the output is computed. In Keras, after designing a model, you need to call the compile method. The compile method plays a role in determining how to reduce the loss in the training process of the model. In the previous lecture, I explained that when backpropagation is performed, the gradient is calculated and a new weight is set using the gradient. There are several ways to set a new weight, and the function that defines a new weight is called an optimizer. You do not need to understand the optimizer functions, but you just need to know that the optimizer function called Atom or the optimizer function called SGD are used a lot recently in the backpropagation process of artificial neural networks. There are several methods for calculating the loss as well as the method for calculating the weight. Loss is not simply the square of the error, but can be defined in other ways, and the function to find the loss is called the loss function. Usually, the loss function used depends on the task type of the artificial neural network. For example, in a binary classification problem, a function called binary cross entropy is used as a loss function. Like the square of the error we learned last time, the loss function has a positive correlation with the error. The loss functions also do not need to be understood mathematically. Just remember that different loss functions are used depending on the task. When training a model, you may want to check how accurate the model is. In Keras, accuracy is not displayed while the model performs backpropagation based on input-answer pairs. Therefore, if you want to know the accuracy of the model while training is in progress, you must pass a list including the string accuracy to the parameter metrics of compile method as an argument. However, there are cases where the metric of accuracy cannot be displayed in tasks other than binary classification. Before all AI models we will implement in this course, the model's performance can be evaluated with accuracy. Now, let's take a look at the compile method code. This code sets a new weight with the optimizer function called Atom and finds the loss with the binary cross entropy function. And the accuracy of the model will be printed during the model training. Model training proceeds by calling the fit method after calling the compile method. Unlike TensorFlow 1, if you call the model's method fit without passing the model to the session, the model is trained. Batch size is the amount of training data loaded at once when training the model. In general, artificial neural network model training is performed on the GPU device. The VRAM capacity of the GPU device is generally less than that of DRAM, and when the weights of the model are loaded on the GPU device, the amount of data that can be fed on the GPU device is further reduced. Therefore, the model must be trained in a way that continuously sends batch size of input-output pairs in DRAM or storage to the GPU device. However, for the data we're dealing with today, the model size is small and the amount of data is not large, so it is okay to specify a large batch size. However, as the size of the model or training data increases, the batch size should be reduced due to the limitations of VRAM or DRAM capacity. In a computer, the CPU and GPU are usually located in different places. Besides, large-scale artificial neural networks are mainly loaded on NVIDIA graphics card. The data we load is stored in our computer's DRAM, and when model training is performed on the GPU device, batch data of the training data stored in DRAM is moved to the VRAM of GPU, and the weight of the model is updated by the GPU based on this data. In addition, weight values are also stored and updated in the VRAM of the graphic card. Since the deep neural network model has a lot of weight information, the space in the VRAM to store the input-output pair data becomes even more scarce. In other words, when loading a large-sized input-output pairs into VRAM, it is not possible to load a large batch. And as the size of the model increases, the data stored in VRAM, such as weights, also increases. So there are cases where a large size batch cannot be sent to GPU. Now, let's see how the fit method is called in the program we wrote earlier. First, input data and output are used as variables. Then, training is performed on all training data 300 times. The batch size is set to 1024. When the fit function is called, the model is trained, and you can check the progress on the console. After training, we will learn how to use the model to make inferences. Before adding the new code after the fit function, create a file called validation text and save it in the same folder as the banknote data and code. Then, write the following data in that file and save it. You can also check the validation data on the course website. If you check the text file, you can see that the class values are 0101010101. We can put only the measurement values of validation data into the model, and we'll be able to test the model by comparing the output of the model to the correct answer we know. Add the code shown in the slide to the code file and run the code again. First, the data is read, and the test input and test answer are separated from this data. And the test input enters the model after model training, and the program will print the values returned by the model. In Keras, you can perform inference using the model.predict method. However, the code in the slide looks a bit odd. It is not a method we made, but it is set as an official method to obtain the inference result of binary classification in Keras. This code means that if the output of the activation function of the last layer of our model is greater than 0.5, the value is converted to 1. And if it is 0.5 or less than 0.5, the value is converted to 0 and returned. NumPy provides a function called asType to change the type of data in ND-array. Since the output of binary classification should be 0 or 1, in our code we cast the output of the model to an int type. If you add the code, run all the code again from the beginning, and print the result value to the screen, you can see that the model's inference result is also 0101010101 and matches the correct answer. This is the end of today's lecture. Next lecture, we will learn about image classification and TensorFlow 2.